Good morning, everyone. Today we are going to study one of the most successful optimization algorithm inspired by nature, that is simulated annealing. So before we discuss about the algorithms, have you ever seen a blacksmith heating the iron and it glows into red and then they will cool it down gradually, right? So the answer why we have to do it, cool it down gradually, why not immediately? So the answer lies in how atoms rearrange themselves to form a stronger crystal structure. So computer scientists borrowed this idea to solve optimization problems. So by the end of this lecture, you will understand how the simulated annealing is used in artificial intelligence, machine learning, robotics, cloud computing, and cybersecurity. So if you just see what is annealing, you could understand that it is a heat treatment process used to improve the mechanical property of the metal. So it involves heating the metal to a high temperature as red hot as you see here in the picture, and then bringing to that temperature, and after that it is cooled down very slowly. So why do we have to do it? The main goal is to reduce the internal stress, improve the ductability, increase toughness, and produce a more stable crystal structure. So metals like steel, copper, aluminum, brass, and gold are undergoing such a process in industries like automobile manufacturing, aerospace, railway engineering, electronics, and construction. So these are some of the use cases where they use annealing, right? So if you see that why annealing is necessary and why do we actually need annealing is in order to overcome the manufacturing defects, because manufacturers will have this rolling, foraging, welding, casting, some distorted atomic structures will be there. So in order to avoid that, we will use this. And there may be also some internal stress, excess hardness, brittleness, and micro cracks, reduced flexibility. And the solution is obviously we have to exhibit or we have to make these metals to go through a rigorous process of annealing. That is by heating and then relaxing. This internal stress can be resetted, okay, and the metal stability and ductability can be restored. So to start with, let's take a small example. So imagine maybe you take a small wire. Initially, you try to bend it, it will not bend, but eventually you try to keep on bending it. Eventually, it bent, and at one level, it just breaks. Okay. So why? Okay, why is this happening is inside the metal, the arrangement of atoms is changing every time you bend it. So initially atoms are arranged a beautiful crystal lattice. As you could see here, it is arranged in a fixed position. It has an arrangements. It has low internal energy, high stability, and strong bonding. So as a mechanical force is applied repeatedly, the atoms moved, right? It got displaced, all right? And then some atom leave the empty spaces called vacancies, and some squeeze into the neighboring positions, and some layers become misaligned, produced dislocations. These defects will increase the internal energy. And initially, when they were organized, the internal energy was low, but now it increases. So this nature dislikes this high energy states. Nature always try to reduce the energy. This simple observation is the foundation for simulated annealing. In our optimization algorithm, we are not moving atoms, instead we are moving the candidate solutions. Poor candidate solutions corresponds to crystal defects, and good candidate solutions corresponds to stable crystal structure. So nature will try to repair the atom. So our algorithm also repairs the solution. So solution in the sense you search for the best solution, you search for the best answer, like how ants search for the food, how birds search for its a place for its nest, right? So a search option is what you call here as a candidate solution. So there are three stages of annealing, where we have stage one is the heating. The metal is heated above its recrystallization temperature. So typically For steel, it is 700 to 900, and copper 400 to 650. So the metal becomes so flexible. Okay. And what happens to the atoms? The atomic energy is measured. The average kinetic energy of the atom increases according to the formula E is equal to 3 by 2 kT, where K is the Boltzmann constant and T is the absolute temperature. So at lower temperature, you can observe that the atoms are very organized, and at the high temperature, they are disturbed, right? So this effect of heating, okay, this effect of heating makes the atom to move freely, and it makes the atom mobile, okay? And the second stage is called as the soaking stage. Okay. So heating alone is not sufficient. The metal is held at the high temperature for a period of time. So this is called soaking. So allow the atom enough time to rearrange. So initially they are very much defective like this, and after sometimes they organized themselves, right? So they maintain, this is called soaking. So why is this soaking necessary? Because atoms need sufficient time to move and rearrange themselves. So imagine, suppose I give you only 1 minute and I ask you to write the examination. So the performance is obviously going to be poor. But if I give you sufficient time, of course, you can reproduce what you have studied. So similarly, atoms also require sufficient time during soaking. Defects become disappearing, vacancies reduces, and atom gradually finds a better position, right? So this now come to this energy landscape graph that is shown here. So you see that there are possible crystal structures available, all right? So each valley represents a possible crystal structure. The nature attempts to reach its lowest energy, because you see that when the atoms are organized, they are in the lowest energy, right? So it will always attempt to go to the lowest energy. So sometimes what happens is they may settle down in a shallow local minima. Obviously, the global minima is somewhere else, but it may try to settle down in a shallow global minima. So in that case, every valley is represented as a candidate solution. So the optimization, like how the simulated annealing soaking process tried to find out the best candidate solution or the best valley, the inspired algorithm also will try to find out the best candidate solution, right? So next step is the cooling process. Okay, so why do we have to cool? There are two type of cooling process. One is the rapid cooling, the slow cooling. Rapid cooling is extremely from 900 to 25. Okay. So you will have a high internal stress, the brittle material, there may be chances of fracturing, and there can be many defects as well. But the recommended is the slow cooling, where you will move from 900 to 700 to 500, 300 to explore every possible time for rearranging the atoms for themselves, right? So that is, they keep on, when the cooling process is happening, they keep on searching for the better position until they just settle down in a high stable crystal structure, right? So this is called the slow cooling. The slow cooling is always recommended, because the high temperature, then it comes to the medium temperature, then it comes to the low temperature, where the atoms are locked into a stable crystal like structure, right? So the slow cooling is one of the most recommended process for the annealing. So until now we saw about the process of annealing, right? And now we need to really understand, why do we need annealing? Okay, and we should understand what is its relationship with optimization. Now let us consider the hill climbing. We have already studied that in the AI. So suppose you are climbing a mountain. Your rule is very simple. Every step you take must move forward. Okay, you never need to walk downhill, but you have to move up to reach a peak. So is this the highest peak of the entire mountain range? Okay, so can you say this? No, the answer is no, because there may be some other highest point in your neighborhood. Okay, somewhere else in your neighborhood. This is exactly what happens in the hill climbing. So hill climbing always accepts the better solution and rejects the worst one. So now imagine another traveler. He reaches the same peak but decides to walk downhill for a shorter distance. After crossing a small valley, he discovers an even taller mountain. Okay, so now a person, the condition is you cannot move downhill. In that case, obviously you will settle down in a local optimum. Okay, you cannot move downhill means you cannot explore another mountain which is really higher than this mountain. But now if you give an option for the player to move downhill, as of this case, okay. So now what you can do, he can again move uphill to explore the next height. Again move uphill to explore the next height. Okay. Now this key innovation introduced a control probability to accept worst moves, allowing exploration to the other hills. So this is how the annealing works. You cool down, then you allow the atoms to settle, okay, so that it becomes so stable. Okay, but you gradually cool it down. You never say, okay, I'm going to take a very steadfast step to cool it. No, gradually cool it down so that it settle down. The same way, when you are searching for a solution in your search algorithm, okay, you can just get this idea of simulated annealing. Okay, you can slowly move downhill as well, like how the slow cooling process is happening in simulated annealing. Here also you can cool down, then again you can heat up and cool down. So one time what happens is you will reach the global optimum. Okay, that is the main idea of simulated annealing, right? And now moving on, the simulated annealing terminologies. We should understand the simulated annealing terminologies. So what is the first terminology is the energy. All right. So there is something called internal energy. Okay. When your crystal is so organized, your internal energy is not sufficient. It is low, right? But when it is disturbed, your energy level is bigger. Okay, so energy measures the ability of a system to perform a work. So we call it as an internal energy. Okay, so the internal energy is measured, or the internal energy is determined by means of the atomic vibrations, molecular motion, and chemical bonding. So scientists usually call that as E. So this energy is equal to that of something called objective function in the optimization problem. Okay, so this equals to the objective function in the optimization problem. So the second one is you call it as a temperature. Okay, so higher temperature means higher vibration, lower temperature you will have a lower vibration. So whenever your metal is cool, it always try to stay in its own position. But when it is heated, you will have a vibration, you will have a movements. Okay. So the average kinetic energy, there is a mathematical relation between energy and temperature. It says E is equal to 3 by 2 kT. Okay, so when temperature increases, the atomic energy increases, and there is also a random motion. So what does this temperature says? So whenever there is a high temperature, there is an exploration phase going on. Exploration means searching for a better solution. Okay, so that is what, whenever there is a high temperature, it happens. But whenever there is low temperature, the algorithm exploits. What is exploitation? Be in a position and find out, is there any best solution available near it. Okay, so that is what is called exploitation. So this is a second terminology called the. So the next one is an entropy. Entropy measures the disorder. All right, so when you say it is neatly arranged, the entropy is low. When it is disorganized, the entropy is high. Similarly, higher entropy will always have a random arrangement, and lower entropy will have a lower arrangement. So how do we compare that with a search problem? So higher entropy means you have many possible solutions, and lower entropy means your search solution is, or your search process is focused, right? And next, coming on to the equilibrium, thermal equilibrium. So the thermal equilibrium, you see that suppose you place a hot coffee in a room, okay, and what happens is sometimes the coffee become chill. What has actually happened? The hot coffee has dissipates its heat to the room, okay. So how can you just compare that with a search algorithm? So initial solution, eventually you search for a better solution. And again, what happens is at one point of time, you just settle down in the best solution. So this is what is the next terminology, the thermal equilibrium, right? And probability. We have to match this with the probability, right? At the last, it comes to the probability of acceptance with the simulated annealing. Next comes the probabilistic search, because you take in hill climbing, you just do a deterministic search, and then you settle down in a local optimum and you stop there. But simulated annealing is not that case. It just go up, down, up, down. It measures the probability of success in every region. Okay, the star you can imagine like probability of success in every region. And once the probability of success is highest, then that is accepted as the answer, right? So you say that you cannot predict it. Okay, atomic movement cannot be predicted exactly. So you can define it using the probability. Okay. So stimulated annealing uses the probabilistic based search. So mathematical foundation for simulated annealing, the acceptance criteria. So on which note you will accept this solution in the simulated annealing, okay, is defined by means of probability of acceptance is equal to exponential e to the power of minus delta c by t. So delta c is the cost change, the change in the difference in quality between the new candidate and the current solution. Temperature T, okay, so it regulates the overall search randomness. Whenever T is high, okay, so when T is large, the exponent approaches to zero, making P of accept is equal to zero. Then it means that it behaves like a random walk, okay, allowing a broad exploration of the search space randomly. Okay, so because high temperature always executes a random movement of atoms. Similarly, in optimization also, it randomly searches for the best solution. Very rigorously, it searches for the best solution randomly. Whenever low temperature, okay, so means P of accept is equal to zero, then what happens here is like a greedy hill climbing. So it refines the local features to converge. So already it has settled down in a place, and from that search space, it will find out which is the best one. So that is what is this acceptance probability. So let us take a numerical example. Suppose the current cost is 50 and the neighbor has a cost of 55. The temperature is 100. So you compute the delta E is equal to 55 minus 50 is equal to 5. And probability is e to the power of minus 5 by 100, which is 95.9512, which means that the chance of accepting the worst solution, okay, is 95 percentage, because the cost is 50. So the current cost has to be obviously accepted. So 95 percentage I will be accepting the current cost. So let us take this case where the temperature is 10. Okay, the probability decreases because the temperature is lower. Okay, now there is only 60 percentage chance. But when the temperature is 2 again, so you see here that only 8.21 percentage chance for accepting the worst solution. So these are some of the numerical examples of acceptance probability. Okay, now what are the components of simulated annealing? We'll discuss that. So initially, a solution should be formulated. The simulated annealing algorithm. Now, we are going to discuss in terms of computer basis. So far, we are talking in terms of metal, right? And we are mapping that with optimization. Now, we are purely talking in terms of simulated annealing applied to a computer concept. How can we apply to it? So it begins with its optimization process with any feasible solution. First, you arrive at a solution. For example, I say that in a traveling salesman problem, I decide on A, D, B, C, E. And similarly, feature selection, I just have the binary mask as 10101110. And cloud scheduling, I say virtual machine 2 to task 1 and virtual machine 5 is allocated with task 2. So this is a initial solution formulation. Then the second step is you form a objective function. What is an objective function in the traveling salesman problem? I have to reach the destination in the shortest time. So f of x is equal to distance. And what is the machine learning? In machine learning, if I use the feature space, my validation error should be less. Similarly, in CPU scheduling, my waiting time should be less. So the second stage is you have to formulate an objective function. And the third stage is you have to generate a neighbor. All right. So what is a neighbor? Maybe a slightly modified alternative for your already formulated solution. So initially you are formulating a solution, right? So a slightly modified version of it. See here, A, B, C, D, E, and the swapped one is A, D, C, B, E. So D and B are swapped. Okay, so I'm just swapping these two. Similarly, we are executing a small bit flipping here and job swapping also. So J1, J2, J3, J4. Instead of that, I say J1, J4, J3, J2. So this is a process of neighbor generation, a slightly modified alternative. And the next one is you calculate you fix the temperature schedule. Okay, temperature controlled randomness during optimization. Initially, high to search globally, then it decreases gradually. So the temperature is initially set to be high, then it just gradually reduces to zero as you are doing in the annealing process. So when your temperature is high, it will have a random exploration phase. Okay, and when you're gradually cooling down, it will just go for a exploitation phase. Okay, so it will search for the best solution very near. Okay, then you have to set the acceptance criterion. So what is acceptance criterion? Delta, that is what we learned in the two slides previously. P is equal to e to the power of minus delta t by t. Okay. Now, after you just create an acceptance criterion, so if the candidate cost is lower, it is instantly accepted. So worst solutions are accepted using probability. All right. Now, after you calculate the probability of acceptance, you generate a random number R. Okay. If R is less than P, then you accept it. Otherwise, you reject it. Okay. So how do you accept that neighbor? You generate a random number R. If R is less than P, yes, or else no. So there are three types of cooling. One is a linear cooling. Linear cooling means it reduces the temperature linearly, 100 to 90, 90 to 80, 80 to 70, okay, with a constant value C. And geometric cooling will allow the cooling process with a decaying factor of alpha, where alpha is between 0.8 to 0.99. And the logarithmic cooling, it iteration index, okay, so it is rarely used due to its runtime complexity. We say that the new temperature is temperature of old divided by log of 1 plus I, right? So it is computationally intensive, so we are rarely using. These are the three types of cooling schedules. So if you think about overall, you will initialize the solution, you will search for the best candidate, you will evaluate it, and this evaluation is similar to that of a cooling period. Okay, so you will gradually try to find out, is there any better, using the probability of acceptance, you will find out, is there any better solution nearby. So this is a complete flowchart of the flowchart and the pseudocode of the simulated annealing function. You generate an initial solution, you set initial temperature, you generate neighbors, you calculate the cost delta E of moving from the old one to the new one, and then you will have accept it. If it is less than 0, greater than 0, you will compute it, generate a random number. If R is less than probability, you accept, otherwise you reject. Then you reduce the temperature. Okay, then whether it has reached the stopping condition, no means again, you find out the next neighbor, do the same process, and again. So gradually you will be finding out. First, initially you will do an exploration, you will settle down in a place, and then you will search out for the nearest neighbors, calculate the cost, and find out which will be the best solution. So advantages is it escapes the local optimum, simple implementation, it's memory efficient, flexible. But the limitations are the cooling schedules, because the T, it depends on the user. So the cooling schedules affects the performance. Slower convergence, because you have to find out for all the neighbors. So parameter tuning is required. So there are a lot of parameters used. So like T, delta E, the cooling schedules and all such. So the parameter tuning is required. So no guarantee that it will reach the global optimum. There is no guarantee that stimulated annealing will reach the global minimum. So there are few variants of annealing as well. So one is a fast simulated annealing. So fast simulated annealing is, it depends on the cooling strategy. Okay. So what is its fast means? FSA uses a cooling schedule that is linearly inversely proportional to time, specifically designed to accelerate the convergent process. We saw a limitation that it is slow convergence. So the cooling is made it so quick through longer jumps. Okay. It is not gradual, but it is longer jump. Okay. So that is what is the fast annealing. Then adaptive simulated annealing. So the cooling process, there is a self-tuning parameter process available here. So addresses the classical weakness of the parameter sensitivity. There is a parameter T, delta E. So the parameter sensitivity is overcome by means of adaptive simulated annealing. So now if it checks the probability using the current value. If it is working out well, then it take over. Otherwise, it uses the next set of parameters. Likewise, it adjusts its parameter such as the cooling schedule, step selection based on the algorithm's actual progress during the search. The next one is the parallel simulated annealing. So to overcome the computational bottleneck of the classical algorithm, parallel simulated annealing leverages modern multi-core architecture. So PSA involves running multiple independent instances of simulated annealing algorithms simultaneously on parallel processors, right? And during the execution, these parallel instances can occasionally exchange their best found solution with one another. So they also exchange with one another, finding out it best. So where are these simulated annealing used? It is used in logistics in order to track the routing. It is used in hardware design, VLSI routing, bioinformatics for protein folding, and artificial intelligence for tuning. So in this chapter, we discussed about simulated annealing. It remains as a robust, flexible tool for global optimization. While it is computationally intensive and sensitive to cooling schedules, more variants like fast, adaptive, and parallel simulated annealing has been discovered.